everyone. You're watching the 15th lecture in the series Mathematical Methods for Economics. This series is part of the e-Gurukul lecture series organized by the Consortium for Educational Communication. The topic for today's video is exponential functions. Exponential functions constitute a very useful class of functions that have a wide range of practical applications. You'll find these functions coming up in discussions of economic growth, population growth. In fact, these functions underlie discussions on economic growth, population growth. Then if you do a course in finance, if you've done a course in finance, then you would know that one of the first things that you're taught in a course in finance is how interest accumulates over time. And here again, the principle of compound interest, exponential functions, these come into the picture. In the sciences, moreover, we use exponential functions to examine the decay of radioactive materials, and also in epidemiological studies where we want to examine the occurrence or development of a disease or a health related event. Before we move to the details of exponential functions, let us first be clear as to what we mean by exponential functions, what exactly the phrase exponential means in exponential functions. So if we want to understand what it means for a quantity to grow or for a quantity to decrease exponentially, here we are saying that a quantity increases or decreases exponentially if it increases or decreases by a fixed factor per unit of time. This phrase fixed factor here is very important. And to make you understand what we mean by fixed factor, let's take two scenarios here, scenario A and scenario B. In both these scenarios, I have two variables, x and y, right? Now, in both these scenarios, x represents time because typically exponential functions are used to examine situations where a quantity changes with respect to time. Now, to see how the y variable changes with respect to time, let me put in a little story here to give you some perspective. So, for example, let us suppose you upload a video on YouTube or Instagram or any social media platform. Then you would like to track the number of likes that you get for your video. So let's suppose we are in scenario A. In this case, so in both scenarios, y represents the number of likes you get for your video. In scenario A, and let's assume time here is measured on an hourly basis. So we are tracking the number of likes on an hourly basis. So in scenario A, in the first hour, you get 2 likes. In the second hour, but at the end of the second hour, you have 4 likes, then you have 6 likes, and so on. So what do you notice here? In this case, the number of likes change by the same amount in every subsequent time period, right? So you get in the first hour you have 2 likes, in the second hour you have 4 likes, so that is a difference of 2. Then in the third hour, 6 minus 4, again a difference of 2, and so on. So what we are saying here is that between any two consecutive y values in scenario A, the difference is the same. Y changes by the same amount between any two y values. So this is what we have in scenario A, which we're going to represent as linear growth, right? Now, what happens in scenario B? Scenario B is a little different. What do you see here? In the first hour, you have 2 likes. In the second hour, you have 4 likes. In the third hour, you have 8 likes. Then 16 likes, 32 likes. What is happening? If you take the ratio between any two y values, you see that the ratio is a constant. The ratio here is 2, right? 4 is twice of 2 here. Then 8 is twice of 4. Basically, your number of likes are doubling in each time period. And this is an illustration of an exponential relationship. What we are trying to say here is that if we take the ratio of any two consecutive numbers, that ratio is a constant. So we have a fixed factor. The value of y in any period is twice the value of y in the previous period, right? So this is what we have in scenarios A and B. Scenario A corresponds to a linear relationship, which in this case mathematically amounts to is captured by the equation y equal to 2 times x, whereas scenario B represents what is known as an exponential relationship, which is to say that you have a quantity which increases in this case by a fixed factor, in this case which is 2 per unit of time. Right? So what is the difference between a linear relationship and an exponential relationship? A linear relationship is one where a quantity increases or decreases by the same amount per unit of time. An exponential relationship is one where a quantity increases or decreases by a fixed factor. So you have a constant percentage between any two numbers, and that is why we say there's a fixed factor between any two numbers. That is the idea of an exponential relationship. And here one would certainly have your video, one could certainly say that your video will very soon become viral, because as I will show you towards the end of the video, by 20 hours or so you will start hitting 1 million likes, and you will certainly qualify for having your video go viral. So you're really going to be popular that way, and that is what we have in this kind of a relationship. Graphically, a linear relationship is represented by a straight line. The slope is constant, so you can see here y changes by the same amount per unit change in x. Whereas the exponential relationship is reflected by the kind of curve that you have here in red. And here you can see that things are slow to start with. The graph rises slowly initially, but for higher values of x, the y values increase rapidly, and you could even have explosive growth. So this is the idea behind exponential growth. To give you another example, in this case, in this new example, I have taken the fixed factor to be 3. And here I am looking at how an infection can spread during the outbreak of a disease. We're in the middle of the COVID-19 pandemic, and if you're following the news, you must have seen that the newspapers have been reporting the number of active cases that are resulting every day, the number of new fresh coronavirus cases on a daily basis. These are being reported. Now, what exactly is happening? And let us assume, to keep things sensible here, let's assume that infections haven't peaked yet. So you have a situation here where, let's say, each person infects 3 other people. So you have day 1 here, where on the first day 1 person is infected, right? Then day 2 he infects 3. He or she infects 3 other people. Then day 3, each you see. So what you see, day 2 you have 3 new infections. I'm tracking here the new coronavirus, the fresh coronavirus cases on a daily basis. So day 2 you have 3 coronavirus infections. Now if each one of these 3 people spread the infection to 3 more people, what will happen? You will have 9 fresh cases on day 3, right? 3 times 3. And then again, if each one of these 9 people spread the infection further to 3 people each, then on day 4 you will have 27 infections. So here you see, this is an example where again you have geometric growth, where again you have exponential growth, and here the fixed factor is 3. So if you take the ratio between any 2 consecutive numbers for any 2 consecutive days, the ratio is fixed at 3. Okay, so let's get down to some math now. I hope I've given you, I hope you've got a sense of what we mean by exponential. We're just saying that the quantity increases or decreases by a fixed factor per unit of time. Mathematically, an exponential function, let's say it's represented as f, it is defined here as f of t equal to capital A times small a to the power t. And here we are assuming that both capital A and small a, lowercase a and uppercase a, are positive constants. We'll just talk about why these are positive constants. Now, what I'm going to argue here is that this lowercase a is precisely the fixed factor that we were talking about, that when we say a quantity increases or decreases exponentially, and that is to say it increases or decreases by a fixed factor. So we are going to argue here that this this a, lowercase a, is actually what represents the fixed factor mathematically. Okay, so let's see how things work. Now, as I just said, f of t, an exponential function, takes a form f of t equal to capital A times small a to the power t, where both capital A and small a are positive constants. Now, at the risk of sounding repetitive, because I have mentioned this point in the last two lectures as well, but because it's an important point, let me reiterate that if you look at an exponential function, then unlike a power function where the base is what varies, the independent variable appears as a base and it is a base that varies, in an exponential function the base is a constant, right? So this little a here, which is the base here, small a is a constant. The independent variable appears as the exponent, right? So it is the exponent that varies. Here our independent variable, we are defining f as a function, the function as a function of time, and here the independent variable we are writing in terms of time. We could even put in an x here, but because exponential functions are usually typically used to examine situations where a quantity changes with respect to time, I've used time as the independent variable. And here the domain is the set of all real numbers. So in this context, let's just try and get a sense of why we take capital A and small a as positive. So the reason why we take this lowercase a, which we'll just say is a fixed factor, we'll just argue it's a fixed factor, why that is positive is, the reason for that is similar to what we argued in the lecture on power functions. The idea being that because t can be any number on the real line, so your t could be a number like half, right? And if t is equal to half, then you'll be in a situation where you're taking the square root of this lowercase a, small a, right? And we all know that we can't take the square root of a negative number. We'll be in negative territory then, and we'll be dealing with imaginary numbers then. So if we are taking t equal to half, then we have to restrict this lowercase a to be greater than or equal to 0. Right? Similarly, t could be 0, and if t is 0, we know that this little a can't be 0 because 0 to the power 0 is not defined, right? So in order to avoid getting into these kinds of situations, we take this a, which we are going to argue is a fixed factor, to be positive. Now, why do we take capital A as positive? Capital A could also be negative, don't worry about that, but the point is that when I show you the graphs of exponential functions, you know, there are these general properties which we want to convey, and capital A being positive preserves those general properties. If we take capital A to be negative, it just means that the graph is just going to flip, because once you have capital A as positive, you're going to have the graph lying everywhere above the x-axis. So it will just mean that if you take capital A as negative, the graph will just flip to the other side of the x-axis. That's all. So it's just manipulation which you can make in your analysis. Right, now coming to the analysis of this small a. Let us suppose we want to look at the value of the function at time period t plus 1, right? F of t plus 1, note here please, is equal to capital A times small a to the power t plus 1, right? I'm just substituting t plus 1 as the independent variable instead of t. And this then can be separated, this expression can be separated and written as capital A times small a to the power t times small a, right? And we know that capital A times small a to the power t is nothing but f of t. So, f of t plus 1, the value of the function at time period t plus 1 is nothing but small a times f of t, right? And this is important because what we are saying is that the value of the function at time period t plus 1 is the number a times the value of the function at time period t. So, if you take the ratio of the function at time period t plus 1 and divide that by the value of the function at time period t, that ratio is going to be a constant, which is nothing but small a, and that is why we say that it's a fixed factor, right? And that is exactly what I was showing you in the examples, that in the case of an exponential relationship, for any two consecutive numbers we have a constant ratio. Also note that if I look at the value of the function at time period 0, f of 0, that is nothing but capital A times small a to the power 0, right? I'm putting t equal to 0, and that in turn is equal to capital A. So, this capital A also has an interpretation. It is nothing but the initial value of the function. It is a value of the function at time period 0. So, therefore, we can also write the function f of t as f of 0 times small a to the power t. So, here do you notice here we've come up with two important results. We've given an interpretation to small a, which is a fixed factor, and we've given an interpretation to capital A, which is the initial value. Okay, let's move on. Now, this is another important result. We are going to argue that if this fixed factor represented by small a is strictly greater than 1, then the function is strictly increasing. However, if it is between 0 and 1, then the function is strictly decreasing. Now, how is that the case? See, if we look at the difference between the values f of t plus 1 minus f of t, we just argued in the previous slide that f of t plus 1 can be written as a times f of t, right? So, f of t plus 1 minus f of t can be written as a times f of t minus f of t. And that is nothing but, if I take f of t common, that is nothing but a minus 1 times f of t, right? So, this now look at the interpretation here. This is really nice, because this is saying that the difference in the values between any two consecutive time periods. So, if we take time periods t and t plus 1, the difference is a minus 1 times f of t, okay? Now, f of t is clearly going to be positive because we are taking capital A and small a to be positive. So, if I have here that a is strictly greater than 1, then clearly f of t plus 1 minus f of t will be positive, right, because a is greater than 1. So, if f of t plus 1 minus f of t is positive, that is to say that f of t plus 1 is always going to be strictly greater than f of t. Okay, so that is to say that in every subsequent time period, the value of the function in every subsequent time period is always going to be strictly greater than the value of the function at time period t, right, whenever a is greater than 1. Now, if a is between 0 and 1, what will happen? A minus 1 will become negative. Now, if that happens, then f of t plus 1 minus f of t will become negative, right? And in that case, we'll have that in every subsequent time period, f of t plus 1 is always going to be less than f of t. So, that is to say the function is strictly decreasing. Okay. Alternatively, if you have done some calculus, you could also get at this result by taking logs on both sides of this function and taking the derivative. So, we have log of f is equal to log of capital A, these are natural logs I am taking, ln, plus t times natural log small a, right. So, if I take the derivative on both sides with respect to t, because I want to see whether the function is increasing or decreasing with respect to time, I have 1 by f prime of t is equal to natural log A. And if you know the properties of natural log, anyways, let me just back up. So f prime of t is equal to f of t. I'm just cross multiplying by f of t. So that is capital A times small a to the power t times natural log A. And if you've studied logarithmic functions, so here we have that if a is strictly greater than 1, then ln a will be positive. But if a lies between 0 and 1, then ln a will be negative. Capital A times small a to the power t will always be positive. So the point here is that here again you can see an alternative way of proving that if small a is greater than 1, then the function is strictly increasing. If it is between 0 and 1, the function is strictly decreasing. So, but the point is, if you haven't done calculus yet, if you don't know it, you can skip this part and just focus on the difference between f of t plus 1 minus f of t. Now, I will quickly just show the graphs for the corresponding values of a, the two cases that I've taken. So, you can see here that when a is strictly greater than 1, the function is strictly increasing, right? Also notice that here the domain is a set of real numbers, right? T can be anything on the real line. The intercept here is 0, a. Also, if you notice whether it's a strictly greater than 1 or a between 0 and 1, the function lies everywhere above the x-axis, right? So, here you can see when a is strictly greater than 1, the function lies here. The range is the range of values that the function can take are between 0 to from 0 to infinity. The range is the open interval 0 to infinity. So, the graph lies everywhere above the x-axis. And here when a is strictly greater than 1, the function is increasing throughout, and also notice the function is increasing at an increasing rate. So, it is increasing slowly to start with, but for larger values of t it increases rapidly, and you could further have explosive growth. The second diagram on the right of the panel is the case where you have a strictly decreasing function because a lies between 0 and 1, and that is the case where you have exponential decay. I'll do an illustration for that, and this is to show situations where your populations are shrinking, populations are declining.